I'll address some of the limitations that we need to be aware of when we interpret data from this AI-based studies. So we learned a lot about deep learning this afternoon, and why it is deep. It is deep because it involves multiple layers. And the concept of neural network here is about inputs, outputs, and the multiple layers in the neural network basically is used to identify, to detect features. And the predominant types of neural networks are the convoluted neural networks, or CNN. And all the studies right now particularly in ophthalmology, most of these studies are based on CNN. But what is CNN? What is convolution? Convolution in CNN is performed on the input data with the use of a filter or a kernel to produce a feature map. So convolution is about merging of data, the merge between the input data and the filter. Here is an example demonstrating how we can apply a filter to extract features. Imagine here we have a 2x2 image map digitalized. This is the input. And the filter we apply is something expressed in the matrix. And what we learn about neural network here is convolution is about merging the filter and the input. And basically is the multiplication of these two matrices. And by extracting the features here, we are getting a new input to the next layer of network. Here is a cartoon illustrating how we can apply a filter to extract features. Here we are interested in, for example, outlining the edges of the picture, and different filters would enable us to identify specific features of the inputs. In this illustration, we learned that the deeper the layer we go through, the more abstract the feature is. In the initial layers of the network, we usually can identify, for example, outline of certain objects or the color of the objects. So these are the superficial layers. But when we go deeper, the information becomes more abstract. So neural network is about extracting all these individual features, and these individual features are then encoded, compared with the input to get an error rate. And through this back propagation, the neural network modifies its weights, modifies filters, and then we would have an estimation of how accurate, how sensitive or specific the performance is. Here is the very first paper, one of the very first papers, illustrating how a neural network can be applied for detection of glaucoma. This paper is actually not designed to detect glaucoma. We learned about this from Daniel's talk. It's based on a DM screening network, but we are also detecting AMD and possible glaucoma, which is defined as capture-to-this ratio more than 0.8, or the presence of a narrow neuroretinal rim, or the presence of a retinal fiber defects. So we're detecting coexisting condition in the DR screening program. And what we learned from this paper is that they applied the CNN, they use transfer learning, CNN. In this paper, the architecture is a VGG, or Visual Geometry Group in Oxford. It called it 16 because this CNN got 16 layers. The numbers here are not so difficult to understand, which I already mentioned earlier. There are many filters in this neural network. All these filters are in the size of 3x3, so these are the matrices, these are the filter supply. And we have 64, for example, here of these filters in the first layer, and then another 64 filters, and then it go through these 16 layers of neural network, and then it get an answer whether there is or there is no possible glaucoma. I just highlight the performance for glaucoma detection here, and this paper show a pretty good diagnostic performance for detecting possible glaucoma. We have an AUC area under the receiver characteristic curve of 0.94, which is a pretty good diagnostic performance indicator. If you have 1, that means the discriminating power of the neural network here is 100%. If it is 0.5, that means it's 50%, 50%, and basically it's by chance for the discrimination. The sensitivity and specificity are relatively high. And then we have another paper. This paper was published in ophthalmology and is done using data collected from China, using fundus photographs to identify, to detect glaucoma. Again, it's a very simple neural network determining whether there is or there is no glaucoma using fundus pictures. And in this paper, they use the GoogleNet, which is another kind of CNN. The architecture is a little bit more complicated. It has 22 layers. In addition to that, this neural network includes the inception modules, which you see there are loops, and there are many boxes in the network indicating that the information is passed not just sequentially, but also there are these modules where you have information running parallel. They're convolution running parallel in these inception modules. So they apply this GoogleNet, and again, they observe pretty good diagnostic performance, AUC of about of 0.96, 0.98, and with sensitivity and specificity more than 92%. And then we have a new paper which was published just a month ago. And this time it's not just about determining whether there is or there's no glaucoma, but it's about using fundus photograph to predict average retinal nerve fiber thickness. So they used retinal nerve fiber thickness measured by OCT, and then they compared with the neural network predicted average retinal nerve fiber thickness. And again, this paper used the Microsoft ResNet. Again, is another type of CNN. And what they found is that they observed pretty high correlation between the predicted nerve fiber thickness and the actual measured retinal nerve fiber thickness. And the coefficient of determination in this analysis is about 0.7. That means 70% of the relationship can be explained by this linear relationship. And what they also observe is that the average retinal nerve fiber thickness predicted by neural network has performance comparable to the actual average retinal nerve fiber thickness measured by the spectral domain OCT. So they didn't find a significant difference in the area under the ROC curve. So I can end the talk by saying, well, AI has a high sensitivity and specificity for detection of glaucoma. But is it really the case? So when we interpret the data presented by this paper, we need to understand what are the limitations of AI for glaucoma detection. All these studies rely on fundus photograph to determine glaucoma, to predict retinal nerve fiber thickness. But we know color fundus photographs actually is not enough, is not sufficient for evaluation of the retinal nerve fiber defects or to assess new retinal rim dimension. Because retinal nerve fiber layer and new retinal rim, they are three-dimensional structure. And fundus photograph are basically two-dimensional structure. So we are not able to get the additional dimension of the optic disc structures just using fundus photograph. And that's why when we look at the false negative examples demonstrated from this study, we can see that those examples, here are two examples illustrating to you AI would not be able to tell you the retinal nerve fiber defects, And there are also false positive cases where in eyes with large optic discs, where you have large cup, this eye could be falsely labeled as glaucoma. And again, in eyes with myopia, AI would fail to identify the true diagnosis. And this is some, again, case examples from the paper by Medeiros. And in this paper, he used fundus photograph to predict average retinal nerve fiber thickness. And we are looking at examples demonstrating underestimation and overestimation of the retinal nerve fiber thickness in these two case examples. Again, what we observe here is that when we have big cup, AI tends to underestimate retinal nerve fiber thickness, but when we look at the actual retinal nerve fiber thickness, in this case, in the right panel, the retinal nerve fiber thickness is actually pretty normal. And then in eyes with relatively normal looking neuroretinal rim, again, AI would fail to accurately predict the average retinal nerve fiber thickness. So these underestimation and overestimation explain why there are 30% of variance that would not be able to be predicted accurately by the AI. And then another issue that we need to be aware of when we study these papers is that is the ground truth for training neural network reliable? All these papers, they rely on professional glaucoma specialists to label whether the optic disc photograph is normal or glaucomatous. But we know fundus photograph actually is not very reliable, even among glaucoma specialists, in determining glaucomatous changes. And we know the inter-observer agreement of optic disc evaluation is actually moderate. And this study done by Dr. Jampel in Hopkins demonstrated that even among glaucoma specialists, we have poor agreement in evaluating optic disc changes. So if we have poor or moderate inter-observer agreement, we would expect the AI would also have poor to moderate agreement among different networks trained in different centers or by different groups. And we also know that's why optic disc photography is rarely used as a reference standard in the diagnostic studies for glaucoma. We usually would rely on visual field as a reference standard when we compare structural measurements for diagnostic evaluation of glaucoma, and optic disc photograph because the sensitivity and specificity for identifying glaucoma is not that reliable. Would OCT be a future of AI instead of optic disc photograph? It can be. Here is a paper done by Dr. Hood. This is not a deep learning paper, but he is using a concept called hybrid deep learning. He adopted the Alex length and using the same weights of this neural network, put the outputs of the neural network into a random forest to come up with parameters to help differentiate glaucomatous from non-glaucomatous eyes. The field is exciting. We're seeing a lot of AI-based technologies being FDA approved. In ophthalmology, we have we all heard is the IDX has been adopted even in the healthcare system in the US. The future is promising, but we need to be aware of the potential limitations. Thank you.